Hello friends, it's Ben again, and this is a video for the differential calculus class. We are looking at the notion of absolute extrema. That's kind of a fancy phrasing to just mean maximums and minimums on an interval. So the base notion of that is that anytime you have a continuous function and a closed bounded interval, the ones with square brackets, closed bounded interval, the ones with square brackets, the function has to take on its maximum value, and it has to take on its minimum value. And so what we're going to need to do is to develop a process for figuring out where those happen at. So let's see whether I can get the iPad to share the screen today. And if so, we will. Okay, if so, we will show something on the screen. Huh. Well, interesting. So when we can't share to the screen, our alternative is to plug in, hopefully, to something else. And let's see whether we can get it that way. All right, and now I'm going to try sharing screen. No, I don't want to do anything with iTunes. Sorry, folks. Sometimes you have to figure it all out as you go. Connect your phone or iPad. Yes, trust this computer. Okay, trust. All right. I told it to share, and all right. Plug it in again. And sure, continue. Yes, I totally love iTunes, whatever. Okay, to allow access, please respond to my iPad. Okay, trust. So apparently you have to trust iTunes in order to trust anything else. That's super. Okay. And let's turn on airplane mode. Yeah, I don't like the way this looks. Oh, well, what can you do? So, okay, I apologize, but please be patient because I'm having iPad problems. All right. Well, better now than tomorrow morning. So, all right. Yep, here we got it. Although I would like it if it were going to make this. Wow. Okay. This is absolutely dreadful, but it's the best I've got. So we're looking for these absolute extrema, and we're going to have a continuous function, and the maximum and minimum are either going to happen at a critical point or an endpoint. So our process is to identify critical points. Oh, that was supposed to say points plural. All right. There might only be one, but there's sometimes more than one. Then we're going to evaluate f of x at the critical points and the endpoints. Find the max, find the min. That's what there is to it. So let's see what we can do with this particular one here. And so we've got our f of x being that. So our f prime of x is going to turn out to be 3x squared plus 2x minus 1 That's not undefined anywhere. And so you're going to set this equal to 0. And so that's going to be something where it's necessary to use the quadratic formula for it. Maybe we can, could we factor that? No, let's see. It would have to be a 3x, an x, and if we had a +1 and a -1, yeah, we can do that. So that's a little bit easier if you can get it to work. I know everybody loves the quadratic formula, but those are our points, all right? And those are the only things we have to worry about. We're going to say f of 1/3. We're going to say f of -1, because those are both in the interval. If they weren't in the interval, we would just throw them out. But we also have to say f of -2 and f of +2, because those are the endpoints for this interval. So f of 1/3 is 1/27, oh my, plus 1/9 and minus 1/3, 1/20. So that means that the least common denominator is 27ths, and you'd have 1 plus 3 is 4, so minus 5/27ths. F of -1, you would have -1 plus 1 minus a -1, so you end up with 1. F of -2, you'd have -8 plus 4 minus a -2, so you end up with a -2 out of that. F of +2, you have 8 plus 4 minus 2, so you end up with 10 out of that. So our smallest, our least value is here at that end, and our maximum is here at that end. And that's it, okay? If you had more than one occurrence, then you would draw your arrow to more than one of them. So, all right, can I get this to turn the other way? I cannot. All right, that's fine. And I thought that was going to take more space, so I'd reserved some more room. All right, so this one we're looking at the extrema for a different function, but we're going to tackle it the same way. G prime of x, and so you have a 2 times, that square root means we'll have a 1/2 of the stuff to the -1/2 power. You subtracted 1 from the power, and then the chain rule says we have to take the derivative of what's inside, so you get a 2x out of that. And then minus the derivative of that x is just 1. So this turns into what? 2's cancel, and we end up with 2x over the square root of x squared plus 1 minus 1. Now, this cannot have a division by 0 error because x squared plus 1 will always be positive. So the only place that this can be a critical point is if this is equal to 0. Since it's not just one big fraction, we can't just set the top equal to 0. So we'll set this equal to 0 and then transfer the 1 across. We can then cross multiply and get that 2x needs to be equal to the square root of x squared plus 1. And then if you square both sides, you have 4x squared equals x squared plus 1, which says that 3x squared is equal to 1, which says that your x is plus or minus 1 over the square root of 3. Now, the thing with that is that we have interval from 0 to 2. So we only have to worry about x equals 1 over the square root of 3. Okay, that's all we've got for critical points. Now we plug in g of 1 over the square root of 3, g of 0, and g of 2. right? So in doing that, I might need a little more space here, so I'm going to take and shove that out of the way. And we will have 2 times the square root. The x squared will be 1/3, so you would have 4/3 in here. And then minus 1 over the square root of 3. So that means that you end up with what? 4 over the square root of 3 minus 1, so 3 over the square root of 3, which is the square root of 3. If we need it to refer to it later, we'll have to note that square root of 3 is about 1.7, okay? Then for g of 0, you'll have 2 times the square root of 0 plus 1, so 2 times 1, minus the 0, so we end up with 2, which is more than the 1.3, or the 1.7 for the square root of 3. Then g of 2, we have 2 times the square root of 2 squared is 4 plus 1 is 5, so 2 root 5 minus 2. Man, I do not know how much that turns out to be offhand, so I grab a calculator and check, and this is about 2.47. And I said this one was about 1.7. I guess with this one down here, we could have said it was about 2.5. That'd be close enough. So this is our absolute minimum. The smallest value the function takes on is square root of 3. And this would be our absolute maximum here at 2 root 5 minus 2. It's about 2.5. Okay, so all the other x values give you something between those. All right. Okay, so now we're going to do the extrema for x squared e to the x. Now this is one I think that you've seen on a problem before. You have to use the product rule for it. The derivative of the x squared is 2x, leave the e to the x alone. Now leave the x squared alone, derivative of e to the x is e to the x. If that were e to the minus x, then you'd have to use a chain rule. But the way to handle this is probably to see that we can factor out an x, and a 2 plus x, and e to the x. So that's not undefined anywhere, so we set it equal to 0. We get it x equals 0 or x equals minus 2, all right? So those are our critical values. E to the x can never be equal to 0, so we didn't get any contribution from that. Now we'll have to figure out h of 0, h of negative 2. Notice negative 2 is still in our interval. We didn't have to throw it out. So h of negative 3 and h of 0, because those are the endpoints per interval. Oh, ha! I'd already listed h of 0, hadn't I? So no need to do it twice. H of 0 will plug back in and just get 0. H of negative 2 will plug back in and get 4e to the minus 2. And I will have to do that on a calculator. And I'm getting about 0.5 from it. And then we'll have to check the minus 3. So that will end up being a 9e to the minus 3. So 9e to the minus 3. I'm getting about 0.4. Okay. So this says that this is our absolute minimum, and this is our absolute maximum. Okay. So, all right, this will be the last one here. I was thinking these would be a little bit rougher than this. But now for this, we tackle it with the s prime of x. That'll be 1 minus 2 times the derivative of sine is cosine. That's not undefined anywhere, so we set it equal to 0. And solving, you get cosine x is 1/2. And then you have to think about the reference angle for that is a special angle of pi/3. And so you would end up with your x being pi/3, or the other possibility is 2 pi minus pi/3, which is, I guess that's 5 pi/3. Okay. So now s of pi/3, s of 5 pi/3, s of 0, and s of 2 pi. That would be all we need to do. So keep in mind with these, we are plugging into the original function, not the derivative. I know it gets confusing because of the local extrema, we had to do things with the derivative. All right, pi/3 minus 2 times the sine of pi/3 is square root of 3/2. So we are going to end up with pi/3 minus the square root of 3. And again, I fear I can't do that in my head. And so I will get about negative 0.7, okay? If you're looking here and saying, oh my God, Ben is not doing more digits on this, because there's not really any reason to, okay? All right, the sine of 5 pi/3 is negative square root of 3/2. So for this, we have 5 pi/3 plus the square root of 3. So plus the square root of 3, I'm getting about 7, it's like 6.9 something. So then I'm going to plug in 0, and I'll just get 0. And I'm going to plug in the 2 pi, and I'll get 2 pi minus 2 times the 0 for the sine of it. And I can approximate that to be about 6.3 without looking it up on the calculator. So this one is going to be our absolute minimum, and this one is going to be our absolute maximum. And that's that. So if what you're thinking is, man, these are easier, why don't I get to do those all the time? You do. We are, before too long, going to come upon something where I ask you to look for some optimization problems to work out. By optimization problems, what I mean is applied problems, excuse me, applied problems where it's got something relatively real world in it, and you're trying to find maximums and minimums of functions that show up there, okay? And your presentation is going to be explaining the calculus of it, along with doing the calculus of it, all right? So that is going to be our activity that we have during final exam week. We have one more exam to go, and then we'll get to shift over to those things, all right? Shouldn't be too rough. But this shouldn't be too rough either, okay? All right, I will see you all in class. Hopefully you're ready to rock when we start on this in the morning.